Okay, let's go ahead and get going. So, go ahead and share my screen. Okay, so just jump right into it. Basically, um, we're just gonna go right in. I got Maple pulled up here. Um, Start it off. So, we're just gonna be using the Laplace command in Maple, which is something new, but nothing crazy. Basically, what this is telling you is that the Laplace command is a part of this integral transform package, which has a collection of the different integral transforms, which we see down here. We get the Fourier transform, Fourier cosine transform, Fourier sine transform, the Hankel transform, Hilbert transform, the inverse Fourier, inverse Hilbert, inverse Laplace, Laplace, Mellin transform, inverse Mellin, and then a couple other things here that I think are just part of Maple, like add table, save table, setup, etc. So they show us here the syntax. Basically, you're going to put in the expression, which is, like for example, cosine or t, and then you tell it the first variable and the second variable, where the first variable is the original uh, expression, what variable the original expression is with respect to. So in this case, t, and in our case, variable two would be s. But obviously, like different types of transforms use different things. Um, like the Fourier transform might transform from t to omega instead of t to s. Just depends. Um, but that's just syntax. So we'll go ahead and just get started. Um, this is how you call the Laplace. So we don't have to actually copy and paste that. We'll just go ahead and do this command real quick because what that's going to do is that's going to go ahead and import all our stuff that we need, just like in the PDF. And now we're just going to try it with um, sine of AT, and we'll go ahead and break through or break down what this is doing. So it's telling you to take the Laplace transform of sine of A times t, where the original function is a function of t, and we're going to transform it into a function of s. Hit enter. There we go. And so now here, excuse me, we're going to do that same thing again, but instead we're going to do it for a group of functions. And in Maple, it looks like you can just comma separate them and then semicolon uh, outside of the squiggly brackets to do the Laplace with these expressions. So you're defining the expressions here and then calling them inside where you would call the function like above. And then it does all of them and generates them all at once. So that's nice. So there's that right there. They're a little bit out of order, but it's not a big deal. Um, they're out of order here and they end up out of order here, but I think they just organize them. Uh, I think that the software organizes it themselves, but you just make sure that you're aware that like, you know, the Laplace transform of t cubed is not, or sorry, of t cubed e to the 3t is not 1 over s minus a. That's the e to the at. This one is actually this right here. Because it's 3 factorial over 3 to the n or s to the n plus 1, but then you got to plug in that s minus 3 because you have that e term multiplied by it. So just get good at recognizing those. Um, and again, this is just an exercise to make sure that they verify with all the ones that we have. Um, this one, for example, is now we're going to do it with respect to x and lambda instead of t and s. Sorry, I'm stealing. Um, so now we'll just go ahead and do that, plug that in. So that's just going to write our equation, right? And then we're going to do the Laplace transform of that equation. So here in the code line here, we're defining equation here, and we're just calling equation. Then instead of t and s, we're using x and lambda. And I guess in Maple you have to write out lambda because there's no key for that, which is that's how LaTeX works and Python. You just call it what it is. And so same kind of deal as above, just different variables. There you go. Um, and then again, we're gonna do that again, but uh, we're gonna call it. We're gonna assign the function the name h, and then we're gonna take the Laplace of h with respect to t, and then just, these are just kind of just the same as what we were doing the last couple times, just using uh, this idea of the Laplace command. But it seems that the Maple syntax is all the same or similar, works similarly. Um, and it's saying that we have to evaluate h at t to obtain the Laplace transform. And so it, it's telling you that it's returning the Laplace transform of expressions only and not functions. And so uh, we are looking at here, we talked about this the other day, how the Laplace transform of h prime and h double prime of t are these guys here, which we know. And where this here, this funky thing here is basically just saying s times big F of s, because we know the Laplace transform of h of t is, I guess, big H of s. They're using h instead of f. Um, but same kind of deal. Um, this is basically, we're calling the LAP underscore DH is basically telling you to that they're just naming the function uh, for the first derivative of h and computing the Laplace transform of that. And that's just how we're naming it. And so again, just more syntax stuff to get familiar with. And so like you can see, it's just doing the first derivative of it. Okay. And she wants you to do these things. Question at and the question D, which we'll do real quick. Again, it'll tell you what it's doing, like before. It's a calling sequence. Um, and then the question D, that's a capital D is a derivative operator, which tells us here. Again, it's another type of calling sequence. Cool. So now we're doing a similar kind of thing. Let me see. Oh, I see. So it looks like what this is doing is it's cutting terms. Yeah. And it's showing that if you subtract one from the other, it's going to give you zero, which makes sense. So we'll just go ahead and do these real quick. Again, I think this is just an exercise in kind of seeing what Maple is going to do. Whoa. What I wanted it to do. Oh boy, that pasted a bunch of crap that I didn't need. Okay, there we go. Yeah, I think I highlighted some stuff I didn't realize I had highlighted. It just like threw everything for a loop. There there we go. And then this is just the simplify command where it's just gonna do uh this is what we got for LAP underscore DH2, and this is what we got for LAP DH, and it's just basically saying, okay, if we subtract one from the other, it's gonna simplify to zero, which is what we expect. So that's all that's saying. And so plug that in and get zeros. Cool. So now we're going to look at the inverse command, which runs exactly the same. Um, expression var1, var2. You just put I and V in front of the plus. Coolio. Um, and then similar like what we were doing before, we're going to call this list containing all the expressions above A, and then we're going to convert the inverse of A. Um, I guess this map thing just formats it properly, I suppose. Um, they're out of order again, but it's fine. Uh, cool. So, or no, they're not out of order. Sorry, they're in order. Anyways, so again, we'll just these these assignments are just a lot of copy and paste the lines of code into Maple and make sure that Maple runs it properly. Get yourself familiar with the syntax. So when we get to the end, we can do the calculation she wants. So now she wants us to do the inverse transform of this guy. So you would just have to type it in. Um, and what it's saying is to make it a little easier on Maple, we can go ahead and have Maple do a partial frac decomposition. Um, and so it says that you could do that with convert. These names are irrelevant. They're just how you're calling the function. You can call this Bill and you can call that Fred. Doesn't matter. You're defining it as this. Just have to make sure you call it like that. And so basically, this is cool because that means Maple can help you check your partial fraction decomp if you need it to, which is nice. Uh, so again, we're just gonna um, define this expression here as f, and then we're gonna define fp, which I guess is just her shorthand of saying the function with the partial fraction command, and then you're calling it as f using parfrac and saying it's with respect to s so that Maple, excuse me, knows to convert it with respect to s, and then bam, because it does it for you. So that's cool. Um, and this is basically just saying you can use the help thing to see how convert can be used in different ways. We check that out. That'd be cool. Um, and again, it's just showing once that's done, it makes it super easy for the computer to know how to invert. Um, and this here, she's just showing you that, hey, you know, you can convert it just straight up based on how you defined F, because Maple knows how to do that, or just for yourself to be able to see it, you can have it also invert it as the converted partial fraction function. You're going to get the same answer, of course. So now we're doing piecewise functions. And so we're going to talk about the calling command. Um, looks like you're doing the first condition, first function, second condition, second function, and then anything else that you need. So for here, it's saying the condition one is it's if it's less than or equal to t, less than or equal to t, 0 is less than or equal to t, or t is less than 3, then it's -1, comma, second condition, t is greater than or equal to 3, it's 1. So that's how you would code in the piecewise, and we're just defining that as f, so that's how we're going to call it, right? Uh, boom. So that does your piecewise, and then we're calling f, and we're plotting it from 0 to 6, so we can see everything. Boom. Measure function. It's a good thing. Anyway, I'm not even gonna say it. I think you see it. You probably see it. Uh, looks a little different than what she's got. So that's weird. Uh, hmm. I've got this bar in the middle, so I'm not sure what's up with that. Because there shouldn't be. It's interesting. Does that format right? Yeah, I guess it did. Hmm. Well, let's see. Uh, it looks like maybe if we do this, something ought to change. Let's see what it does. Yeah, there we go. That goes ahead and gets rid of that vertical line like we needed. I guess it just didn't render on this first graph, which is fine. And yeah, so it tells it to search these continuities and split it into intervals where it's continuous. So that's what that's doing. And then again, we're just gonna compute the Laplace transform of it. Boom, there you go. And then okay, so it's saying older versions couldn't do it, and we have to get used to getting around this by redefining it in terms of the Heaviside function. And there is a calling function for our calling command for the Heaviside, um, called Heaviside. And so what that's saying is um, we can redefine f, or you could use just the convert, and that'll do the same thing. So we'll go ahead and do both of those. Because remember, we called f1, um, or we're calling f1 and telling it to convert into some uh, oh, oh, it's because there, there we go. Okay, and then again, it's just saying, hey, you can go ahead and do the convert call as well, which is cool. Multiple ways to skin a cat, but who the hell skins cats? Okay. Now we're just doing it for F uh 2, right? That's just calling it and then writing out F2. There you go. And then now you can verify that they're equal uh by graphing them, and we're evaluating them. Um, and then you can just do it again uh, using F2, and it'll give you the same answer. So nothing crazy. And now we're going to do the IVP. So I mean, it's more of the same, really, right? We're basically going to apply it to the entire equation, put in the initial conditions, solve the resulting equation, and then find the inverse. And you could do all that using the so basically, uh, it looks like we're just going to define our differential equation. It looks like this is a new syntax to say the second derivative, right? Because we have x double prime plus x equals sine, and it looks like this code is saying, hey, we have our differential equation x of t, where x has two time derivatives. So that's what that is, I'm assuming. However, if you want to check that, do it, but that's what the syntax is looking like, in my opinion. Okay, so there's that. And it basically did out what you would expect it to do, right? You take the Laplace transform of x of t, and then it takes the Laplace transform of sine, and then it also does the Laplace transform. Like this is s times x of 0 plus f of s, and then this is s squared times f of s minus the first derivative with respect to 0. So this is just stuff that we're used to, just written in kind of maple language. Like if you were to solve this by hand, you should get something that looks somewhat similar to this, just with different notation. This will be the same. This always looks the same. The 2 over s squared plus 4, because that's just what the Laplace, right? B over squared plus b squared, right? That looks the same. So now what we're doing is we're going to apply our initial conditions. And upon doing that, Maple is going to be able to evaluate this thing, uh, and now we can start rearranging stuff. Excuse me. And now it's gonna solve it, right? Kind of like we would do by hand, where it's gonna rearrange these f of s's, isolate them, and then divide over whatever's left. And that's gonna be the result, it looks like. Let's go ahead and do that. Boom, there we go. And then just like we would do by hand, we're gonna use the inverse Laplace transform. And looks like the S1, S2, S3 is like step one, step two, step three. So boom, there's our solution. And then now we're going to do that again with our four initial conditions. And so we're going to assign a name to it, right? Give it a call. So we don't have to paste that into everything. And again, same thing like I was saying before, that T money sign for, it just means fourth derivative, so on and so forth. As you can see, that's the same thing here, 4 times diff y of t, comma t, money sign 3. That just means third derivative of y with respect to t. Same thing here, second derivative, first derivative, no derivative. There's all our initial conditions. Cool. So we'll go ahead, paste that, boom. And then we want to do the Laplace transform and substitute in one step. So let's copy this and then break it down. So what it's telling you to do is you're subbing y0 equals 0, which we had here. Y prime of 0 equals 1, which we have here. dy of 0. And then d at 2 means the second derivative at 0 is 1. And d at 3 means the third derivative of y at 0 is 0. So that's just syntax, right? They use capital D because it's the derivative operator. And then at 3 is just Maple's way of saying third derivative. So the operator runs 3 times. Just what it does. Boom. Cool. There's our answer. Um, and then we can combine the last two steps by solving it, right? Solving Q1 um, and then inverting it. So what this is going to do is it's going to move all this stuff over and give us our function of s, and then it's going to solve that function of, or sorry, this solve thing is going to move it over and make it look like this, and then the inverse Laplace is going to take that result and go ahead and tell you the result, the solution to the differential equation. Boom, there we go. Okay, uh, we could also have it equal to Laplace in the dsolve command, and that's showing the advantage in using it to solve an initial value problem. Um, so omitting the option method equals Laplace, so you would say with DE tools, um, then this gives you the first solution, and then it's showing that you can do it again using Laplace, and it'll clean it up, right? So this is how we were doing it last time, just straight up IVP using Maple's syntax. Boom. This should all look familiar, except maybe it's different because we're using the D operator to represent initial conditions, which is a little different, but that's fine. Um, the whole dsolve DE2, that's what we're calling this, and that all is something we've done before, right? And you say RHS to let it know to be on the right hand side of sol one. Again, all that's familiar. Now we're just going to do it again, and it's the same exact syntax. The only thing is we're going to add in that little method equals Laplace. And that's going to let Maple know, okay, I'll solve this using Laplace instead of whatever method Maple would use by default. And again, you can verify that by graphing them or evaluating them, um, or you can convert it into something less complicated. She's just saying it's helpful to try, right? Like you can just do this to clean it up, and then now we're getting to the fun stuff. We got to do yours. Shouldn't be too hard. Um, so we already did this one by hand, and she wants us to decompose it and check it with Maple. So that's easy. Um, really, the only hard part is going to be typing this thing in. So what I'm going to do is I'm going to go back up to the line where we use partial fractions here. So we're going to just throw this in there again. And what we're going to do is we're just going to clean it up a little bit. This, yeah, get that out of the way. Well, let me scroll. That makes me so mad. Like I want this at the top, not the bottom. I hate that it looks like that, but nothing I can do about it. So what we're gonna do is we're just gonna input this into that. So we got 7s squared minus 41s plus 84. So go 7s squared minus 41 plus 84. Boom. There's the numerator. I want to get this out of the way. Can I? Okay, cool. Great. Um, S minus one on the bottom. So we got a whole other function down there. So we've got to clean that up. So it'll be S minus one. And then that, I'm guessing we're going to need a double parenthesis. S minus one times S squared minus 4S. So you do S caret 2 minus 4 times s plus 13. And just to make sure that Maple knows exactly what we're doing, I'm going to go back in and make sure. I guess my computer is running on either a higher software or just looks different. So I'm going to make sure that these square terms and whatever all look the same. And so this is going to take our function f and it's just going to define it. Just going to write it. Oh, that's not right. Hold on. Why is it doing? What the hell? Hello? This is a parenthesis. Oh, come on. Here, let's try this. Maybe Maple's being extra dumb. Oh, there you go, Maple. So you just need a little bit of a hand. So now we have that, and then we'll do that parfrac command. Some more up here. Where are you? Here we go. So we'll do this, but now what I'm going to do is I'm going to call this F1 to differentiate it from what we had before, and then we'll call this FP1, call that F1. Now it's going to decompose that. Beautiful. And then we're just going to take the Laplace inverse. So I'm just going to call this SOL1, and that's going to be equal to INV, LAP, LACE, and we just need our function, which is FP1, comma, the first variable in this case would be S, second variable in this case would be T, and semicolon. Make sure that that's going to work. I'll just check one of these ones we did up here. Yeah, it's going to give us what we need. Boom. Beautiful. Coolio. Good way to know that it's right is that's definitely the correct transform, inverse transform. So, um, sorry, my mom was texting me. Go ahead and knock out the second one. So now we want to solve for y of s given the initial value problem. So we'll go ahead and code in this differential equation, just like kind of how we were doing it up here. So we just need to write our equation, which we'll do like how we did in the last one. So we'll just say EQ2 is equal to, and then I'm guessing the diff, yeah. So we'll do diff y t comma t. I think it was the second derivative. Yeah. And we'll do minus. This has all parentheses on it. Make sure that's right. So it looks like y of t comma t money for y of t comma t. Yep. So that's all in the right boat. Give me a second. No. Do we? Got one too many out here. There we go. And then that would just be plus, or sorry, minus 6y prime. So minus 6 times diff y of t, comma, t, money sign, 1, close parentheses. It's going to take first derivative and then plus 5 times y of t equals t times e to the t times exp t. Remember, you have to call the exponential function by using exp. And then we got to solve it using the initial value problem. So they gave us two initial conditions. And so we'll just go ahead and write that. So there's our equation, just like we needed. And now the way we're going to solve it, right, is like how we did here. We're going to substitute these different initial conditions and do the Laplace all in one step. So if I copy this, throw it down here, we can tweak it. So we'll call this, I guess, IC for initial conditions 2 for problem 2. And we need to substitute that y of 0 equals 2 and y prime of 0 equals negative 1. So y of 0 equals 2 and this one equals negative 1. We don't need any of the rest of it. Get rid of it. Boom. And that comma Laplace is going to do what we need. Hit enter. Oh, hold on a second. We're not using del. We're using EQ2. There we go. Cool. And that makes sense because like this is what it's supposed to be over here. And then we're getting what we're supposed to have over here. So we're just calling equation 2 after we substitute. Coolio, coolio. And then what we're going to do is like we did up here. We're going to just inverse Laplace, have it solve that. So what it's going to be doing is it's going to take this equation and it's going to rearrange it, turn it into a function of s. That's what the solve does, and then it's going to invert it. So all we have to do is just change this to, I believe IC2, because like up here, Q1 was the substituted thing. Yeah, so we just need to call that IC2. And then we're just going to call this SOL2 because it'll be the second solution when it's done. And hit enter. Boom. There you go. This one we just want to check using Maple. And this one again, solve the given third order using Maple. So it's going to be the same kind of deal, right? So we'll say equation 3. Let me do something. Oops, what do I want to do? This in new, yeah. So I can see it. Make this go a little quicker. So it's y triple prime. So we're going to write that as, oh, whoa, hello, wrong tab. We're going to write that, oh no, it's not going to be type it up, is it? Damn it. Yeah, no, it's not. Fucking blows. Okay, well. Oh wait, can't I? It's too much work. I could split my screens because I have my monitor up, but it's not even worth all that work. Y triple prime plus Y triple prime. Let's do that first. So diff Y T comma T money sign 3 plus um, Y, or sorry, diff parentheses Y of T comma T money sign 2. And then I think it's plus 3 times something. 3 times Y prime minus 5Y. So 3 times diff parentheses Y of T comma T money sign 1 and minus 5 times Y of T. And that's all equal to 16 e to the minus T. So equals 16 exp minus T. And so now we're just going to print that. I guess you don't need the semicolon. I'm gonna put it in there. Oh, I didn't use it before, but I'm going to do it for now just to get in the habit of using it. And then it's just going to be exactly what we did before. So what we're going to do is we're going to use our same subs thing here. So at this time, we'll call it IC3. And we have different initial conditions. Now we got y0 equals 0, so that is going to just go to 0. And we've got y prime of 0 equals 2. So this becomes 2. And then the next one is going to be, I believe, d at 2 of y. Does that look how it looked up there? Yeah, you just need parentheses. Make sure one more time. Yeah, just need parentheses. And then of 0. And that's going to be -4. And again, same kind of deal. We just need to change this to equation 3. Boom. And again, same kind of deal. Uh, call the solution, solution 3. And paste this in. So now, same kind of thing. We'll just tell it to solve the initial condition 3 and then all the same stuff. Boom, there's our solution. Cool. So, and if you wanted to see that intermediate step, you could just say rearrange is what I would call it. All right, that might be a command. Just be careful. I'll just call it rearrange equals. And then you could just do this command here. And I believe this will just show you, yeah, where it did everything and solved it if you wanted to see that. How it broke down P for rack or whatever, however it did it to rearrange it. Cool. So I'm gonna call it there because there's only one problem left, and I think armed with all these examples, I think you can do it on your own. I've got faith in you. If you need help, just give me a shout. But that's gonna be all, and see if I can get back in the meeting here. Stop share. Cool. All right. Awesome. See you later, Katie. Hope you feel better.